Imagine that you're a parole officer preparing for a case review. A person who spent several years in prison is scheduled to be released in a few months. Your job is to determine the level of supervision and support that person will need when they return to the community. As part of the process, you're given results from a computerized risk assessment tool. The system has analyzed information from thousands of previous cases, including criminal history, employment, substance use, social relationships, and other factors associated with recidivism. Based on these data, it estimates the person's likelihood of reoffending and identifies areas that may need intervention. This may sound like a hypothetical scenario, but it isn't. Risk assessment and decision support systems like these are used every day in criminal justice settings around the United States. They help guide decisions in local jails, probation and parole agencies, state correctional systems, and reentry programs. For example, the Risk Needs Responsivity Simulation tool is used by over 200 jurisdictions in the United States, ranging from the Rockdale County Jail in rural Georgia to the New York City Mayor's Office of Criminal Justice. Importantly, these systems are not intended to make decisions automatically. They're designed to support professional judgment by identifying patterns that might be difficult for any individual decision maker to detect across thousands of cases. But this immediately raises a difficult question. If the statistical model and a decision maker's professional judgment point in different directions, which should they trust? More broadly, how should we make predictions when the future is uncertain? Although some of the technology is new, the underlying question is not. Psychologists have been studying this for decades. The findings have led to some surprising conclusions. In many situations, statistical methods perform as well as, or even better than, expert intuition. At the same time, expertise still matters, particularly in environments where people receive frequent high-quality feedback about their predictions. In this video, we'll examine what psychological science has discovered about prediction, forecasting, and expertise. Psychologists and other researchers who study judgment and decision-making often distinguish between two broad approaches to prediction. The first approach is known as clinical prediction, or sometimes called clinical intuition. In clinical prediction, an expert considers the available information and makes a judgment about a particular case. A physician diagnosing a patient, a psychologist evaluating a client, a parole officer assessing the likelihood of recidivism are all examples of clinical prediction. Now, importantly, although the word clinical is here, it doesn't have to be in clinical settings. This applies equally well to a mechanic predicting how long a car is going to last. The assumption behind this approach is that experience and expertise allow people to recognize important patterns and appreciate the unique features of individual cases. The second approach is known as statistical prediction, sometimes known as actuarial prediction. Here, predictions are generated by combining information according to explicit rules derived from empirical data. In some cases, these rules may be relatively simple. In others, they may involve sophisticated statistical models or computer algorithms. The basic idea, however, is the same. Rather than asking, what does my professional judgment tell me about this particular person or situation, the question becomes, what tends to happen in similar cases? And what do the data suggest is most likely to happen here? The distinction between clinical and statistical prediction became one of the central questions in the psychology of judgment and decision-making. In the 1950s, psychologist Paul Meehl reviewed the available evidence and reached a surprising conclusion. Across a wide range of domains, Statistical methods, even simple statistical methods, often performed as well as or better than expert judgments. At first, many researchers found this conclusion difficult to accept. After all, how could a relatively simple statistical model outperform an experienced professional who can consider the unique details of each individual case? That question has motivated decades of research on prediction, expertise, and decision making. Over the decades that followed, researchers repeatedly tested Meehl's conclusion in new settings, including medicine, education, criminal justice, and mental health, and with many different kinds of predictions. The results have been remarkably consistent. Although there are important exceptions, the evidence generally favored statistical approaches to prediction over intuitive approaches. Why might this occur? One of the most common explanations is consistency. Statistical models apply the same rules to every case, and they combine information in the same way every time. Human decision makers, on the other hand, are influenced by many of the same tendencies that affect judgment more generally. For example, we may give too much weight to recent experiences or particularly memorable cases. We may see patterns in small amounts of information or focus on cues that seem important while overlooking information that's actually more predictive. As a result, our judgments can vary from one case to another, even when the available information is essentially the same. Statistical models are certainly not immune to error. A model can only be as good as the data and assumptions on which it's based. But statistical methods often have an important advantage. They apply information systematically and avoid many of the inconsistencies that affect human judgment. This does not mean that expertise is unimportant or that professional judgment should be replaced completely by algorithms. Instead, the evidence suggests that prediction often improves when decision makers make effective use of data and use methods that reduce inconsistency in judgment. The success of statistical approaches raises another interesting question. If statistical methods often outperform intuition, what kinds of information should these methods use? Do we need to understand why a particular variable predicts an outcome before we can use it to make predictions? Some researchers have argued that the answer is no. One of the most interesting ideas in prediction research is called blind empiricism. The basic idea is straightforward. If a variable consistently predicts an outcome, it might be useful, even if we don't understand fully why it works. A classic example in psychology comes from the original versions of the Minnesota Multiphasic Personality Inventory, or MMPI. Some of the questionnaire items in this inventory appeared unusual, to say the least, or had no obvious connection to psychological disorders. Yet researchers found that certain responses reliably distinguish between groups of people. From the perspective of blind empiricism, that was enough. If an item consistently improves prediction, it's useful, even if the underlying reason was not immediately clear. It's important to recognize that the statistical methods studied by Paul Meehl were generally quite simple by modern standards. They often involve straightforward rules for combining information rather than sophisticated computer algorithms. However, the basic logic of blind empiricism has become increasingly important in the age of machine learning and artificial intelligence. Many modern predictive systems are designed primarily to maximize predictive accuracy, even when the relationships they discover are difficult to explain or interpret. In that sense, contemporary artificial intelligence raises many of the same questions that psychologists were debating decades ago. Should we trust a prediction if we do not fully understand how it was produced. Many modern decision support systems use statistical and computational models to assist human judgment. In medicine, computerized systems can compare a patient's characteristics with large databases of previous cases and generate recommendations or possible diagnoses. In criminal justice, risk assessment tools use information from thousands of previous cases to estimate the likelihood of recidivism and to identify factors associated with successful reentry. Importantly, these systems are usually not designed to replace experts. Instead, they're intended to support decision making by providing information that people might otherwise overlook. Increasingly, the most effective approach appears to be a combination of human expertise and statistical tools. At this point, you might reasonably ask, if expertise matters, shouldn't experts naturally become better predictors with experience? The answer is yes, but usually not as much as we might expect. Research has often found that years of experience are only weakly related to predictive accuracy. In many domains, highly experienced professionals make predictions that are only modestly more accurate than those of less experienced individuals or even novices. Research has often found that years of experience are only weakly related to predictive accuracy. This does not mean that experience is unimportant. A 2009 meta-analysis by Spengler and colleagues, for example, found that education and clinical experience were associated with a modest increase in the accuracy of mental health judgments. Decades earlier, Hillel Einhorn and Robin Hogarth had proposed an influential explanation. They argued that becoming a better predictor requires more than simply accumulating experience. To improve, people must have opportunities to compare their predictions with what actually happened, and more importantly, to learn which cues were useful and which were misleading. In many professional settings, these opportunities are surprisingly limited. A clinician may never learn whether an alternative diagnosis would have been more accurate. A hiring manager may never discover how successful an applicant who was not selected would have been. A parole officer would never know what would have happened had a different decision been made. Without clear corrective feedback, people may gain experience without becoming substantially better predictors. This does not mean that experience lacks value. Over time, professionals often develop deeper knowledge of their field, become better at recognizing important patterns, and learn to identify factors that novices might overlook. The challenge is that these gains don't always translate into more accurate predictions about the future. Experience can also increase a person's sense of familiarity and confidence. As we encounter more cases, we often feel that we understand a domain more deeply and can make better judgments. However, unless people have opportunities to learn from those prediction errors, there's no guarantee that greater confidence reflects greater forecasting skill. Psychologists refer to the relationship between confidence and accuracy as calibration. A well-calibrated forecaster expresses high confidence when they're likely to be correct and lower confidence when outcomes are much more uncertain. Research has shown that people are often more certain about their predictions than their actual accuracy justifies. As a result, experienced professionals can become increasingly confident in their judgments with experience without becoming proportionally more accurate. In other words, confidence and forecasting accuracy are related, but they are not the same thing. This has an important implication. We often assume that years of experience are a reliable indicator of forecasting ability. In reality, simply spending more time in a profession doesn't guarantee that someone has learned to make better predictions. The reason, as Einhorn and Hogarth argued, is that experience improves forecasting only when people have opportunities to learn from the outcomes of their predictions. The importance of feedback also plays a central role in the work of Daniel Kahneman and Gary Klein, who've argued that expert intuition is most likely to become reliable when two conditions are met. First, people must have opportunities to receive frequent and accurate feedback about the quality of their judgments, as we've talked about. But importantly, the environment itself must also contain sufficiently regular patterns that can be learned. When both of these conditions are met, experience can lead to genuine forecasting skill. Meteorology provides a useful example. The atmosphere is governed by physical processes that exhibit regular patterns and can therefore be modeled and learned, even though there is always some uncertainty. At the same time, weather forecasters make predictions every day and receive rapid objective feedback about whether those predictions were accurate. Over time, this kind of environment supports the development of both sophisticated forecasting models and genuinely skilled forecasters. Other domains may provide weaker opportunities for learning. In fields such as psychotherapy, hiring, or criminal justice, the relevant patterns may be more complex, less stable, or difficult to detect. In addition, feedback may be delayed, incomplete, or ambiguous, and alternative outcomes are often unknowable. As a result, even highly experienced professionals may find it difficult to determine whether a prediction was correct, whether it was correct for the right reasons, or whether a successful outcome simply reflected chance. This explains why expert predictions are not equally reliable across all domains. Some environments are simply better than others at producing accurate forecasters. The broader lesson is that the quality of a prediction depends not only on the skill of the forecaster, but also on the characteristics of the environment in which that forecasting takes place. Let's return to the question we began with. Imagine once again that you're a parole officer reviewing a case. A computerized risk assessment suggests one course of action, while your professional judgment points in another direction. What should you do? Psychological science suggests several important conclusions. First, predicting the future is inherently difficult because uncertainty can never be eliminated. No statistical model and no expert can know with certainty what will happen in any individual case. Second, decades of research following Paul Meehl's work have shown that statistical methods often perform at least as well as or better than expert intuition, particularly when they apply information consistently and make effective use of data. Third, experience alone does not guarantee accurate forecasting. Whether expertise leads to better predictions depends in part on the opportunities that people have had to learn from outcomes and on the characteristics of the environments in which they make those predictions. Finally, expertise and statistical models should not necessarily be viewed as competitors. Increasingly, the most effective approaches to prediction combine human judgment with empirical data and decision support tools. So, if the model and the expert disagree, there may not be a simple rule that tells us which one to trust. But evidence does suggest a general principle. We should be cautious about relying on intuition alone. We should take statistical evidence seriously, and we should recognize that expertise is most valuable when it develops in environments that support reliable judgment. The goal is not to replace people with algorithms or to ignore the value of professional experience. The goal is to understand the strengths and the limitations of both. Because making predictions about the future is one of the most difficult tasks we face. And good judgment often depends on knowing when to trust our intuition, when to trust the data, and when to use both together. After all, as Yogi Berra has supposedly said, it's tough to make predictions, especially about the future.